Hi, welcome back to AP Chemistry. This is Miss Gray, and we're in podcast 4.4, which is all about calorimetry and heat capacity. You've already learned about calorimetry before. It's simply the measurement of heat flow for a reaction. There's a few ways that we can accomplish this, but basically it relies on the use of a calorimeter, right, which is a device where we can measure the temperature change. Let's review some vocabulary first real quick. Heat capacity describes the amount of heat required to raise an object's temperature by 1 degree or kelvins or Celsius. And so what we mean here is like a droplet of water. We want to raise the temperature by 1 degree. Well, that's going to have a different heat capacity than if I have this great big puddle of water, right? Or a big tank full of water. Then that's going to take a lot more heat energy because this larger object has a higher heat capacity than the smaller object. Yeah, a tiny little drop of water doesn't have the ability to hold much heat. So the greater the heat capacity, then the greater the heat energy there would be required to produce the same rise in temperature. So let's use a comparison that would be fair. Right? The molar heat capacity would describe the heat capacity of a mole of a substance. That way we're always talking about the same amount and we would have a more fair comparison. If we're talking about specific heat though, then we're talking about not a mole, but 1 gram of a substance. As you know, moles can have a different amount of grams or volume even though the number of particles is the same, because not everything has the same density. So specific heat describes the heat capacity of just 1 gram of a substance. Here's how we would calculate specific heat. We measure the amount of heat transferred and divide that by the mass of that object times the temperature change that the object underwent. So as the temperature goes up or down, we multiply that by the mass, and that's how we can calculate specific heat. You're going to do this in your Hess's Law Lab to calculate the specific heat of your calorimeter so that we can account for any heat that was absorbed by the styrofoam cup itself when we do our experiment. So C is the symbol for specific heat. Q is the symbol for heat, and then M, of course, is mass, and delta T is the change in temperature. Remember, when we're talking about change in temperature, it's always the final temperature minus the initial temperature so that you can get the correct sign, positive or negative, in your temperature change. And then that is where we derive this equation then to describe the amount of heat. Q is equal to mc delta T. We used this in class the other day. You're going to use this a lot in your homework and in your problems. The first law of thermodynamics allows us to describe the temperature change for one thing compared to the temperature change for another. Because what we know is that whatever energy is given up by your system has to be equal to the energy absorbed by the surroundings, or vice versa. So to calculate the specific heat of a substance, we don't normally measure the temperature change of that substance. We measure the temperature change of the surroundings in the immediate vicinity of that substance. So we can see what a known mass of the substance will change by when it gains or loses a specific quantity of heat. So what else do we know? Oh yeah. I want to make sure that you understand if temperature change is measured in kelvins, it's equal to a temperature change in degrees Celsius, because converting kelvins to Celsius requires you to add 273.15 to that number, right? Well, if you're adding this same number to your final temperature and your initial temperature, then you subtract the two, it's like you didn't add anything at all. So don't worry about changing kelvins Don't worry about changing kelvins to Celsius for thermochemistry. One of the easiest kinds of calorimetry experiments to conduct are those that are at constant pressure. These are effective because the enthalpy change is equal to the heat change when we're at constant pressure. So the device we use is very inexpensive. It's a styrofoam coffee cup calorimeter. It's used because then the pressure of the system will be the same as atmospheric pressure. We can look up atmospheric pressure that day and we know exactly what we're dealing with. The heat that's produced by the reaction is entirely absorbed by the solution, and we can then apply Q equals mc delta T, where the heat of the solution depends on the specific heat of the solution. Usually it's water, because that one we know, and hopefully you remember that specific heat for water is 4.184 joules per gram degree Celsius. So here's what we know, that if the value of Q for the reaction is less than 0, then that means its sign is negative, right? And that was an exothermic reaction. When the value of Q for a reaction is greater than 0, then of course its value is positive, and that process is endothermic. It's absorbing energy because its energy is increasing as it gains energy from the surroundings. A bomb calorimeter is a different type of apparatus. The concept is the same. We're going to measure a temperature change, but this time we're going to keep the volume the same. This would be most useful when we're using combustion reactions, because a combustion reaction tends to produce a lot of gas, which would create pressure changes. So bomb calorimetry is used to measure the heat in hydrocarbons, for instance, because those are typically measured by combustion. So the heat produced by the reaction is measured by the temperature increase of the water surrounding the reaction. Here's the equation that we would use for this one. It's the heat of the reaction is equal to the opposite in sign, the specific heat of your calorimeter times the temperature change that we measured in the water. Here's what a bomb calorimeter looks like. Basically, you've got to have a place to hold your sample, and so that's what this little cup down here is for. And then this wire goes through it because this is your ignition source. So you want to have your wire touching your sample of your hydrocarbon inside your crucible so that when you're ready to combust it, you have a way of igniting it. Then it's important that you have the water that's surrounding your combustion chamber swirling around. So there's a stir that keeps the water moving around through here. We're going to measure the temperature before the combustion and then the temperature after the combustion so that we can see any change in temperature. And we usually have to use the magnifying eyepiece because, as you can imagine, with a sample inside our steel container, so that the volume doesn't change, the temperature doesn't have a tremendous change. It's just going to be something small, right? And so this is basically what your bomb calorimeter looks like. We're going to burn a fuel and see how much heat it generates. So C would be the heat capacity of your calorimeter. You would use a known standard, a hydrocarbon that we always know how much heat it's going to make, to calibrate your calorimeter so we know how much heat the calorimeter itself is absorbing. Then we can tell the heat of the reaction by the temperature change. The heat produced in these experiments is not going to be equal to delta H. Delta H is only equal to Q when we're under constant pressure. These reactions do not occur under constant pressure. So in this case, Q is equal to the change in energy, not the change in enthalpy. Where volume is constant, work is equal to 0. And we don't have to go through all the math to show that. Let's do some examples so that you see how we handle these types of problems. The specific heat of graphite is 0.71 joules per gram degree Celsius. We are to calculate the energy needed to raise the temperature of 75 kilograms of graphite from 294 kelvins to 348 kelvins. So this is a pretty straightforward calorimetry problem. Q equals m times c times delta T, where we know that the mass is 75 kilograms, and I'm going to go ahead and change that to grams right away. So 75,000 grams. And then C is our specific heat. For graphite it is 0.71 joules per gram degree Celsius. We'll call that gram degree kelvins. Same difference. And then the temperature change is going to be the final temperature, 348 kelvins, minus the initial temperature of 294 kelvins. Now I'm ready to calculate Q. So I'm going to take the mass, 75,000 grams, times my specific heat, 0.71 joules per gram per Kelvin, and temperature change, I didn't calculate that yet. Let's see, 348 minus 294. I did not need a calculator for that. 54 kelvins. Alright, let's just check units. Grams is going to cancel grams down here, and kelvins cancels kelvins. So for heat, we're left with units of joules, and that makes sense for what we know about how to measure heat. So now I'm going to go ahead and calculate out the rest. I get Q is equal to 2875500 joules. That seems like quite a lot, doesn't it? But remember, this is 75 kilograms of graphite, so it's not unreasonable to have a large amount of heat. Let's see, how many sig figs do we get to keep? Specific heat had 2, mass had 2, and temperature had 3. So we better keep only 2 sig figs. I'm going to look back behind this number, 2, 9, then how many? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. There we go. So 2,900,000 joules of heat is required to raise that temperature. That's all there is to it. Q equals mc delta T. Of course, we've got another example so we can see a different way of looking at this type of problem. If we've got a 46.2 gram sample of copper that's heated to 95.4 degrees Celsius, then it's placed in a calorimeter containing 75 grams of water at 19.6 degrees Celsius. The final temperature of both the water and the copper is 21.8 degrees Celsius. The question is, what is the specific heat of copper? So this is a very typical calorimetry type of problem. We did the specific heat of metals lab last spring so that you would have some experience in doing this type of thing. So basically we're saying we're going to take a chunk of copper and we're going to heat it up. We're going to add some heat to it. Then we're going to plunk it in cold water and let it cool down. And as it's cooling down, the heat is transferring from the metal to the water, and we're going to measure how much the temperature of the water goes up so that we can see what's the overall transfer of heat. So we're going to have to use heat for water to get to the heat for the copper. That's the only way to do this here. Alright, so what do we know about the water? Remember, we're using heat of water, so let's take the mass of the water. Let's see, we had 75 grams of water. And then specific heat of water is always the same, 4.184 joules per gram degree Celsius. And then temperature change, final minus initial. Let's see, my final temperature of the water is 21.8 degrees Celsius. My initial temperature of the water was 19.6 degrees Celsius. Let me go ahead and calculate that out. So 21.8 minus 19.6, 2.2. Now let's find the heat of the water. So we take our mass times the specific heat, and multiply that by our temperature change, and we'll get Q for the water. I end up with a heat of 690.36 joules. Now I have not yet answered the question. This means that the water absorbed 690 joules of heat when the metal cooled off. So the amount of heat that was lost by the metal is the same magnitude. But since it lost that same amount of heat, I have to put a negative sign here, right? They're equal in magnitude but opposite in direction for the transfer of heat. So now I'm going to use the amount of heat lost by the metal to calculate the specific heat, C, of my metal. So let's rearrange Q equals mc delta T. This time we're solving for C for the metal. We need to use the values that describe the metal only. So I'm going to solve for C, divide by m and delta T on both sides. So I get C is equal to Q over m delta T. Remember, for this situation, the mass is the mass of the metal now, so it's 46.2 grams for this mass, not the mass of water. And then delta T is the temperature change of the metal. The final temperature was 21.8 degrees Celsius, but the initial temperature of the metal is over here, 95.4. So it was really hot. That's about what we would expect boiling water to be in Falcon, because it doesn't get up to 100 for it to boil. It's usually less. Alright, so we take our heat of the metal, negative 690.36 joules, divide by m times delta T, so 46.2 grams. And delta T, what's our temperature change? Let's see, 21.8 divided by 95.4 should give, oh, why am I dividing? Subtract. Whoops. And we'll get a negative value here, negative 73.6. Alright then, let's go ahead and work out the math. Let me know if you get something different, but here's what I'm getting. I get positive, because I've got a negative here and a negative there, so positive 0.20303 something or other. How many sig figs? Let's see, 3 here, 3, 3, 3, 3, 3. Okay, so 3 sig figs, 0.023. And my units are, switch pen colors so we can see. My units are joules per gram degree Celsius, right? Joules over grams and degrees Celsius. So there's the calorimetry problem that's exactly like what we did last spring, when we conducted the specific heat of metals lab. Great, what's next? Oh, the spinning. Here we go, example 3. A 2.2 gram sample of quinone is burned in a bomb calorimeter whose total heat capacity is 7.854 kilojoules per degree Celsius. The temperature of the calorimeter increases from 23.44 degrees Celsius to 30.57 degrees Celsius. What is the heat of combustion per gram of quinone and per mole of quinone? Alright, well, we've got a strategy for us. Remember, heat and energy are the same in this situation, so we're going to find heat, Q. which is equal to the heat capacity times the change in temperature. And it's, of course, the opposite when we're talking about the reaction releasing heat. Yeah? So, what have we got? Heat capacity of the calorimeter is, where is it? Right here. 7.854 kilojoules per degree Celsius. We're going to multiply that by the change in temperature. So final minus initial, I'm going to take 30.57 minus 23.44. Got to get that decimal point in. Okay, my temperature change was 7.13 degrees Celsius. And that gives me an overall heat during this process of negative 55.99902 joules, of course, because, oh no, not joules, kilojoules, because the degrees Celsius cancels, and I'm left with kilojoules. So be careful though, we did not answer the question yet. Our question says, what is the heat of combustion per gram? Alright, well, if this amount is from 2.200 grams, then how much is for 1 gram? Well, let's just divide. So divide by 2.2, and I get negative 25.4541 kilojoules per gram of quinone. And of course my sig figs need to be checked. Looks like I get to keep 4 sig figs, so 1, 2, 3, 4, negative 25.45 kilojoules per gram. The last part of the question asks how much heat per mole. So you know what to do. We've just got to figure out how many moles this turns out to be for quinone. I'm going to need some more space. Alright, so if I have a 2.200 gram sample of quinone, which I'm just going to call Q if that's alright with you, and even if it's not alright with you, I'm doing it anyway. And I need to know how many grams of quinone are in 1 mole. So I've got to look at that chemical formula. Quinone has this formula, C6H4O2. Alright, so 6 carbons weighs 72 grams. Well, 72.06, right? And then we're going to add 4 hydrogens. And 2 oxygens. So I get a molar mass of 108.10 grams per mole. What should we do now? Let's see. I'm going to go ahead and solve for moles so I can be done with my T table. Let me change grams to moles. So I have 0.02035 and a whole bunch of other digits. That many moles of quinone. And I'm just going to leave that number in my calculator for my next step, right? I had negative 55 point something kilojoules. Now I don't have that number in my calculator anymore. And I don't have a fancy calculator to go back. You guys all wrote it down? You do it. Tell me what you got so I can fix my podcast. But I'm going to take this amount of heat that we calculated before and divide by the 0.02035 moles, because what I'm saying is this heat came from this number of moles, so I want to know how much heat comes from just 1 mole. So we just divide these two. Shoot. I wish I could go back and fix that mess. All right, here's what I ended up with. Negative 2751.588205 kilojoules per mole. And so let's check our sig figs. I get to keep 4 of those bad boys. So that's going to make me round up my last digit, negative 2,752 kilojoules per mole of quinone, which is a typical standard used in calibrating your bomb calorimeter. So, hey, what do you know? We've done 3 examples, and I think that's it. Let me have a look. Yep, sure enough, that is the end of the podcast for calorimetry. Try the practice problems in your packet, and try the problems in your book. Let me know how it goes. See you guys in class.